Good morning and good afternoon, everyone, and welcome to Demystifying and Mythbusting Transient Immunity Testing. My name is Imad Qaddi. I'm Product Manager and Sales Manager at EMC Partner in Switzerland. Here is today's agenda. We will look at where ESD burst and surge actually come from in the real world, and then also review the key standards. In each standard section, we will talk about some common misconceptions, typical mistakes in testing and verification. We will also have a short live EFT verification, and finally time then for questions. Let's first start with one of the oldest test standards, EST. EST is caused by static electricity, which means an imbalance of electrons on a surface. The most common mechanism is triboelectric effect. When two different materials touch and separate, for example, walking on carpet, using shoes with rubber sole, electrons are transferred. The human body is actually a very good capacitor. Simply walking across a carpet can generate up 30,000 kilovolts. That voltage sounds extreme, but the real danger is not voltage alone, it's the very fast, very high current discharge into sensitive electronics. In EMC testing, we model the human body using the human body model, or HBM. The average human body has a capacitance of about 100 to 200 picofarads and skin resistance between 300 and 2 kilo ohms. When a charged person touches a conductive object, for example, a USB connector, the charge is released in a very fast current pulse. Humans usually do not feel EST below 3000 volts, but modern electronics can already be damaged at 100 volts or less. That's the reason why EST immunity testing is absolutely critical and crucial. We will focus on commercial EST standards IEC 61000-4-2. Please bear in mind that there are other standards for EST like automotive standard, military EST standard, or semiconductor standards. The commercial standard has been updated in 2023 and came with new important updates. The test level remained the same, contact discharge from 2 up to 8 kilovolt and air discharge up to 15 kilovolt. The RC network is still 150 picofarad and 330 ohm. A new recommended RC network for wearables has been introduced, which is 200 picofarad, 50 ohm, but it is not mandatory. And the voltage tolerance is 5%, and both polarities must be tested. What really changed is how we verify the EST pulse, especially regarding measurement accuracy and repeatability. According to the new standard, EST generators must be calibrated up to level 4, and for both polarities, 5 key parameters must be measured. The first current peak, the current at 30 and 60 nanoseconds, and the rise time between 10 and 90%, and a new and important addition of peak 2, which is measured between 10 and 40 nanoseconds. We will talk about current peak 2 later on this presentation. In the table, you see 4 test levels up to 4 kilovolt, along with the calibration parameters, values, and also tolerances. However, the generators on the market can go much higher after 30,000 volt. This is the new calibration setup with vertical wall 1.2 by 1.6 meter and the reference ground plane, and also a 2 ohm target and the generator mounted on tripod, for example. The standard also requires a high bandwidth measurement system. The oscilloscope used must have at least 2 GHz bandwidth and a sampling rate of 8 up to 10 gigasamples per second. Let's talk now about the misconceptions regarding EST verification. Not only contact discharge must be calibrated, but also air discharge output must be also considered. According to the latest edition 3, if the air discharge chip consists of passive or active components, an additional calibration between 2 up to 15 kilovolts using the EST target is also necessary. However, the tip is made only from metal or conductive material, only DC measurement using a voltage divider like you see on the picture is actually sufficient. So another misconception in ESD testing, it is often assumed that only the first very fast peak is decisive for testing. However, this is a common misconception. In addition to the first peak, the second peak, which occurs approximately between 10 to 40 nanoseconds, is also very important. If the second peak is not properly controlled or calibrated, it can significantly influence the test result. This means that the device may pass or fail the test, not because of the first peak, but because of the second one. For this reason, edition 3 of the standard has introduced explicit calibration requirements for the second peak, highlighting its importance for realistic and reproducible test results. This parameter is responsible for controlling the common ringing you see on the picture that is caused by all generators. This makes all results between generators and lab comparables reproducible. This slide addresses a frequent error in ESD current pulse verification, the assumption that return cable connection is optional or actually minor. When the return cable is disconnected or broken, the measurement becomes completely invalid. Thus, the testing also becomes invalid. If you look at the measurement result table, the first peak measures only about 2 or 3 amps, whereas the standard reference requires 15 amps in this example. Furthermore, because there is no path for the energy to return, the second peak and current at 30 and 60 nanoseconds drops effectively to about 0 amps. So bear in mind to always make sure that your return cable is properly working, not broken. And if the results are wrong or verification results are wrong, please first check your return cable. It doesn't always mean that the generator is broken or damaged. Another very common misconception is 100 or even 500 megahertz oscilloscope is good enough to capture the ESD pulse. This is actually wrong. ESD pulses contain frequency components above 1 gigahertz. Using insufficient bandwidth results in first very slow rise time, in our example 17 nanoseconds instead of 800 picoseconds, lower peak current 9 amps instead of 15 amps, and completely distorted waveform. This leads to non-compliant verification and could lead to false assumptions that the generator is maybe broken, which is actually not always the case. If you are using a digital oscilloscope, you may check your bandwidth setting or filter and set it to at least 1 gigahertz or better than 2 gigahertz in this case for a verification. Let's move on now to electrical fast transients, EFT, also called burst. Burst disturbances are caused by fast switching events. Typical sources are relays, contactors, switches, and inductive loads, especially also found in households like washing machines, microwaves, ovens, etc. Switching on devices with inductive loads cause rapid change in current, dI over dt, which generates a high voltage spike. An abrupt switch off produces a narrow high frequency transient, which we call EFT or burst. Also, brushed motors and modern PWM motor drives are a strong source of burst-like disturbances in the range up to 100 kHz. Burst is therefore very common in industrial environments. The standard IEC 61004-4 defines a very precise generator parameters. We have rise time is about 5 nanoseconds, the pulse width is around 15 nanoseconds, and repetition frequencies are 5 kilohertz or 100 kilohertz. These are extremely fast signals. That's why small mistakes in test setup, generator grounding can completely distort the waveform. The test levels are divided into power ports test levels and I/O ports test levels. The power ports are normally tested up to 4 kilovolt and the I/O ports up to 2 kilovolts. The frequency is actually depending on the applied product standard. If the standard doesn't specify any frequency, both frequencies should be tested. This slide illustrates the three examples of verification setups for burst testing. To ensure the generator output is within standard tolerances, the verification can be conducted periodically, maybe once a month or every 3 months, etc. is up to test lab to decide. First, we perform the direct EFT output verification. This is a high voltage measurement directly at the generator's output using a specialized 50 ohm or 1 kilo ohm load to verify the poles shaped into different plots. Next, we move to the EFT internal CDN verification. This step is critical because it verifies that the transients are correctly passing through the decoupling network without excessive attenuation or distortion. Finally, for tests using a capacitive coupling clamp, we must verify the test setup as shown in the right picture diagram with 50 ohm load and using also a transducer plate. When the measured waveform appears distorted, it is often assumed that the generator is defective. In practice, this is usually not always the case. In most situations, distorted waveforms are caused by measurement or setup issues such as improper grounding of the generator, incorrect DSO voltage divider settings, missing termination resistors, damaged connection cable, or insufficient oscilloscope bandwidth for bursts. At least 400 MHz bandwidth is required to correctly capture the burst pulse. In addition, when a coupling-decoupling network is used, verification at the generator output alone is not sufficient. The waveform must be also verified at the CDN output, as you see on the picture on the bottom of the slide. The common misconception in labs is that the length of the generator ground cable has no significant impact on the test results or verification. In reality, even cables as short as 30 or 50 centimeters can significantly distort the test impulse. The reason why is because burst pulses have a very fast rise time, 5 nanoseconds as you know, and high frequency content up to 100 kilohertz, which requires a short, low inductance return path. The ground reference plane provides this defined return path. That's why, according to the burst standard, EFT generators must be well grounded and placed directly on the ground reference plane, and an additional grounding, large area grounding cable as you see on the picture must be implemented. This ensures stable, reproducible, and comparable test results between different laboratories. The proper grounding is therefore essential to obtain reliable and standard compliant burst immunity test results, and it's very important for verification. A common misconception in EFT verification is that a standard probe is sufficient for correct measurement. As you can see here, this setup is completely misleading. Without the required 50 ohm load, the test results are heavily distorted. In this example, the peak voltage is measured at 20 kilovolts. That is a deviation of 1900% from the actual value. Pulse width is also completely exaggerated at 190 nanoseconds, an overestimation of 280%. The bottom line, without correct termination, the measurement is simply useless for compliance. According to burst standard, don't rely on standard probes. Always measure with the correct load to guarantee a valid result. This slide focuses on other common misconceptions when verifying EFT and burst pulses. The typical mistake is using an adapter with a long looped ground cable during pulse verification. As shown here, this setup significantly alters the measured parameters. The peak voltage is reduced by nearly 20%, while the rise time increases by almost 280%, and the pulse width is extended by about 50%. These deviations are not minor, they fundamentally change the pulse shape. The conclusion is clear: long or looped ground connections severely distort EFT and burst pulse. This leads to invalid measurements and can result in non-compliant and misleading test outcomes. Proper verification therefore requires short, direct, and low inductance grounding to ensure accurate and repeatable results. Finally, let's talk about search. This slide explains how lightning events create transient disturbances that are relevant for immunity testing. Lightning activity can generate strong electromagnetic fields that couple into nearby cables and conductors, inducing unwanted voltage and current inside the system. They flow through ground paths or through the impedance of connected circuits. Even when lightning discharges directly into the earth, it can still affect installations by coupling into the shared grounding system of the buildings. Not only natural lightning causes surge disturbances, there are other causes for surge like switching surges arising from load contactors or transformer switching. While these have lower energy than lightning, they are repeatable and require testing with 1.2 by 50 microsecond combination wave generator. And also fault-induced surges caused by short circuits or ground faults that induce overvoltages through transformers. To ensure protection, we simulate this using a combined generator, as I said before. This slide outlines the technical specifications for combination wave generator or CWG as per standard 61000-4-5. The generator is defined by two primary waveforms, 1.2 by 50 microsecond open circuit voltage impulse you see on the right side, and also the 8 by 20 microsecond short circuit current impulse, including tolerances for peak, rise time, and pulse width, as you see also on the left side. As shown in the parameters table, the generator must support an open circuit voltage from 500 volt up to 4 kilovolt with an output impedance of 2 ohm. Finally, table 1 details the standardized test levels for line-to-line and line-to-ground configurations, ensuring the device meets requirements up to 4 kilovolt. Here you see the one-phase coupling decoupling network configurations as defined by the standard. All compliant CDNs must fulfill these very basic requirements. All generators on the market have actually an internal one-phase CDN. For line-to-line testing, we use an 18 microfarad capacitor with 2 ohm source impedance. And for line-to-ground, 10 ohm resistor and 9 microfarad capacitor are added, increasing the total impedance to 12 ohm. Three-phase system expands to include L1, L2, and L3. This allows for complex testing between any two phases or from any phase to earth. These definitions ensure the precise, repeatable surge simulation required by the standard. In surge testing, as per IEC 61000-4-5 edition 3, the voltage waveform at the UT port for high currents up to 200 amps is a major challenge. As the UT current increases, the internal decoupling components of the network change, which impact the surge pulse shape. The table shows that as we move from 16 amp up to 200 amp range, the standard allows for broader tolerances in the pulse duration and peak voltage. For example, at the line to PE coupling, the duration tolerance expands from 25 microsecond at the lower current to 45 microsecond at 200 amps. That's why every range must be individually calibrated. This ensures that the 1.2 by 50 microsecond impulse remains within the specified limit, regardless of the rated current of the device being tested. Let's start with some misconceptions. A common misconception is to save time. It's enough to test only the maximum surge level. This is actually not always correct. All test levels up to specified level must be applied, starting with 500 volt, 1 kilovolt, and up to 2 kilovolt. Let's go through an example to demonstrate the issue. If the tested EUT uses, for example, a surge protection at 550 volt, so when you start the test at the max test level of 2 kilovolt, the SPD will clamp immediately and the electronic is protected. Hence, the test is then passed. But if applying a test level of 500 volt, which is below the clamping voltage of the SPD itself, which is 550 volt, the SPD may not clamp since the clamping voltage is higher. Thus, EUT electronic will experience the 500 volt and the EUT may fail the test. This shows it's always recommendable to apply the surge test starting with the main test level of 500 volt and increasing up to 2 kilovolt. This slide addresses a critical practical challenge in search testing according to the search standard, which is the unintended tripping of facility circuit breakers. The common misconception is that tripping breaker indicates a damaged or short-circuited search generator. In reality, this is often caused by the decoupling network CDN itself. The CDNs contain high-pass filters with large capacitors. These capacitors allow a significant amount of current to flow to the protective earth during the impulse. Safety devices like residual current circuit breakers detect this as a leakage fault and trip to protect the circuit, halting the test. So I will present two solutions to prevent circuit breaker tripping. The first one, using an isolation transformer. This is a highly effective method where an isolation transformer is placed between the main supply and the surge generator. By decoupling the test circuit from the building's earth leakage protection, you prevent the surge current flowing to PE from reaching and tripping the facility's RCCB. And the second one is actually a solution using circuit breaker that can be switched off during the search test, and then after completing the test, the RCCB must be then switched on again. This search test actually can be only conducted by trained staff. Please bear in mind that to take always all possible safety precautions to protect the test engineer, since this is very dangerous. A common error in lab setups is the belief that any cable length can be used for short current verification. The picture on the left side shows an incorrect practice using a long cable, in this case 2-meter cable, which can distort the current waveform due to the cable inductance. The measurement shows a rise time of 6 microseconds, which is 24% deviation from the expected standard. The measured peak and also the post duration are also lower than the standard, but still within tolerance. So in this case, make always sure to use a very short cable for verification, as we will see on the next slide. To ensure compliant waveform verification according to IEC 61000-4-5, we recommend to follow these calibration setups you see on the slide. For voltage waveform calibration, using a differential voltage probe is actually highly recommended. Unlike standard probes, a differential probe allows for floating measurements, preventing ground loop that could distort the waveform, even damage your oscilloscope. For current waveform calibration, high response current probe is also recommended to capture rapid current change without saturation, and also using a very short cable. For the short circuit calibration, less than 10 centimeter is recommended in this case, because longer leads or cables introduce parasitic inductance that slows down the rise time and reduce peak values, leading to inaccurate verification. Let's now figure out how to properly verify the EFT pulse using the correct verification setup in a live session. We are now in our demo room, and I would like to show you how to perform EFT verification using the right tools according to the standard IEC 61000-4-4. So this is our setup. We will need, of course, an EFT generator. In this case, we are using IMU-MGS. The generator, as I said in the presentation, is directly placed on the reference ground plane and is also grounded using a very short grounding connection and large area connection. We will also need an oscilloscope. In this case, we are using Rodon Truss RTM oscilloscope, and as I said in the presentation, the bandwidth must be at least 400 megahertz. So this is the verification kit we will use during the verification. We will need 1 kilo ohm load as per standard, and also we will need a 50 ohm load as per standard, and then we do also need a cable for a trigger cable. Okay, let's now start with our verification setup. So we will then connect the load, the 50 ohm load, to the direct output of the EFT, and then we will connect then the other end to the oscilloscope, channel 1, and then also we will connect our trigger cable to the oscilloscope. So now we can start setting up the oscilloscope as we are measuring with 50 ohm load, so we need to select the 50 ohm input, in this case not the 1 mega ohm, that's very important. And then also we go to probe and then use a ratio of 2000 to 1. Let's move on now to the calibration parameters on the generator. Now we can go to EFT. Then the level, we can set the level to 500 volt in this case, positive polarity. The time is set to 300 seconds, it's okay. The repetition is 300 milliseconds. The frequency is 5 kilohertz, and the burst duration is 15 milliseconds. We need also to select the right coupling. We are at the direct output, so we will need to change to the direct output, and then we can start the verification. So here we see a EFT spike, and according to the standard, the voltage level must be verified if within tolerance, the rise time between 10% and 90%, and also the pulse width. And of course, using the scale button on the oscilloscope, you can also verify the burst package if it's 15 milliseconds, and also burst repetition, which is 300 milliseconds in our setting. The same verification must be also conducted with 1 kilo ohm when calibrating the direct output. This is according to the standard. And then, of course, the internal CDN must be also calibrated. For that, we need an adapter and connect it with very short connections, as you see, and it can be then connected to the generator. For example, we can then start with neutral and then move the 50 ohm load to the internal CDN and start the verification. That brings me to the end of the presentation. Thank you very much for your attention and looking forward to your questions.